Okay, talking about stuff that is relevant to some problems that I've assigned that people should know because we've done it, but don't, and it's getting close to final time. So we've pretty much covered all the topics except maybe just a couple, and we want to refine our problem-solving ability. And what we're doing then is kind of summarizing stuff, again, that we should know by this point, but apparently don't. So first of all, projectiles, okay? We know that the acceleration of projectile is this, with the I component and the J component. In other words, gravity pulls things straight down, at least as we perceive it from the surface of the Earth in the vicinity of the surface. There's no, if we set up our X and Y coordinate system, so Y is vertically upward, then we have zero X component to the acceleration for projectile. Now we're talking about an ideal projectile where there's no force in the X direction, no drag force, for example. The kind of projectiles you'd have on the moon, although your acceleration of gravity would be a little different. Okay, so acceleration is no I component, negative 10 meters per second squared J component. It's actually 9.8, 9.81, varies from point to point. We're using 10, it's about 2% high, so you could factor the difference between 10 and whatever gravitational acceleration is at a point into any results you get from this. Just keep track of how this quantity is used. Anyhow, there's your acceleration. Okay, well, acceleration is the rate of change with respect to time of velocity, so that the velocity is antiderivative of the acceleration with respect to time. We integrate and we get this, and I don't have to go through the steps of the integration. We get arbitrary constants C1 and C2. If V of 0 is V0x plus V0, if V of 0 is V0x times the I vector plus V0y times the J vector, then it follows immediately that C1 is V0x and C2 is negative V0y. Now there's a little confusion in this. I explained it in terms of the R function. And just how we get the values of the C1 and C2. In any case, it follows that your V of t is V0xi plus a negative 10 meters per second squared times t plus V0y, all that times J. We integrate that to get our R function because velocity is the rate of change of position with respect to time. We integrate the velocity with respect to time, and the integral is totally straightforward. So we integrate the I component, we integrate the J component. I don't have the J on it. Yeah, I can slide it in there. Kind of a bad looking J, but it's in there. And I don't think I put the J down here either. But the end result. Okay, so we do the integration. The integration is totally straightforward. There should have been a negative sign in front of the 5 meters per second squared. Okay, so we have it. Now, some details. If R of 0 is x naught I plus y naught j, then since R of 0, according to this, is what we get when we put zeros in for t, well, it's V naught x times 0 plus C1, and the negative 5 meters per second squared, 0 squared plus V0y times 0 plus C2. That just becomes C1I plus C2J. And we conclude that since this has to equal this, C1 had better be equal to x naught, and C2 had better be equal to y naught. So that our R of t function, replacing the C1 and C2 by x naught and y naught, is what you see here. So those are the equations for any ideal projectile. Now the model has parameters: V naught x, x naught, V naught y, y naught, and t. These are all quantities that need to be either declared or found. We can generally choose x naught and y naught if we know the initial position. if we know any position of the projectile, okay, if we know enough information at any position, then x naught, y naught would be that position. Let's note that v naught x and v naught y are v naught cosine theta and v naught sine theta, where theta is the angle with the positive x-axis measured counterclockwise. Also, Pythagorean identity, v naught x squared plus v naught y squared equals v naught, which follows immediately from this. If you add the square of this to the square of this, you'll have a v naught squared times cosine squared theta plus sine squared theta. The cosine squared plus the sine squared is 1, so you get the square root of v naught squared, which is v naught. And you should know that. You should have done that and seen that when you learned about vectors, among other things. Okay, another situation, simple harmonic oscillator. Okay? Well, first question we have in a problem about a simple harmonic oscillator was potential energy. Well, we still don't know the definition of potential energy. Okay, well, here's the definition, and it's expanded just a little bit. But the idea is the change in potential energy between 2 points is equal and opposite to the work done by conservative forces as you go from the first point to the second. Okay? So, and I say this can be done along any path from the first to the second, because what's a conservative force? It's a path-independent force. If a force is path-independent, now this is a result from multivariable calculus, and nobody's had multivariable calculus or is taking multivariable calculus right now. But that can be done along any path from the first point to the second. Okay, so that's your change of potential energy. Now, potential energy of a simple harmonic oscillator, first identify the conservative force. Well, for simple harmonic motion, that force is negative kx, and this force is path independent. It doesn't matter if I go from here to there or from there to here. If x is positive, for example, the force is going to be negative. Okay, if x is negative, of course, the force will be positive. Just consider a positive value of x1 and x2. If we go from this point to this point, where the force is in this direction, it doesn't matter if we go from here to here or from here to here. The thing is still pulling us back with the same force at the same point. At any point, the force is the same no matter in what direction we're traveling along the x-axis. Okay, and that's unlike friction. If we push an object against friction from here to here, friction exerts a force this way. If we pull it back this way, force is in this direction. So friction is not a path-independent force. Now, potential energy change from x1 to x2, then, well, the work done from x1 to x2 is just the integral of the force with respect to position, and the negative of that is the change in potential energy, because it's equal and opposite to the work done by the conservative force. So it's a negative of this integral. And of course we can write the integral, and we really should have just written it this way, and it's totally straightforward to do the integration. We see clearly that we get this. There are other ways to see this, and actually more informative ways, but we'll stick with the integral. Okay, well then, the potential energy at, let's say, x sub f, relative to the equilibrium point x equals 0, is just the potential energy change from 0 to that position xf. The integral from 0 to xf negative kx dx. We do the negative of that because it's equal and opposite. We get 1/2 kxf squared, so the potential energy at x, at any general x, is 1/2 kx squared. So if we're looking at the energy situation for a simple harmonic oscillator, it oscillates with an amplitude A from position x equals negative A to position x equals A, where x equals 0 is the equilibrium position. Potential energy at this point is 1/2 kA squared, because of course if x equals A, That's what you get. And over here, it's 1/2 Ka squared. If you square negative A, you get a positive A squared. And of course, potential energy is 0 at our reference point, the point with respect to which we measure our potential energy. So we have a potential energy function. Our potential energy function is nothing but a vertically stretched y = x squared graph. In other words, just a parabolic graph with a vertex at the origin. And here's a picture of potential energy versus position x. Okay, there's a parabola. Maximum potential energy occurs at A, 1/2 Ka squared, and at negative A, again, 1/2 Ka squared. So there's our potential energy function. There's a graph, and if you know how to use graphs, that can be very handy. Now, then, given the mass of your oscillator, your work energy theorem tells you that your work energy theorem is used to obtain the kinetic energy at position x. Now, you're going to have to think about how to do that. And then the kinetic energy at position x can be used to conclude the velocity at position x. Now, the problem that we're talking about pulls all this together. What we know is the equation of motion for simple harmonic motion is derived by mx double prime equals negative kx, mass times acceleration, net force, equals negative kx. That's the condition of simple harmonic motion. And this we divide through by m, get x double prime equals negative k over m times x. But we don't know how to solve this differential equation, or if we do, we're not assuming it in this course. But we can know that this is the solution. And we can pretty easily reason this out. We did this in the first week of class. That this is going to have to be a cosine of something, and we struggle with the chain rule a little bit, because nobody comes out of first year calculus knowing it. But, you know, work that out, got over that hump pretty easily, so that you can at least verify that this has to be the solution and have a good idea why we use this function, because the cosine and the sine are the only functions we know about whose second derivative is a negative multiple of the function itself. Take that insight together with simple harmonic motion, we can reason this out. At minimum, you need to know this, and you need to know that this is a solution. Where omega is, of course, equal to the square root of k over m. Okay, well, this implies your velocity and acceleration functions and your circular model. And all those need to be used anytime you work with simple harmonic motion. You need to pull all these ideas together. You need to have all these ideas accessible to you. And if you do, you have an excellent foundation for understanding simple harmonic motion at the level of this course. If you can apply it to a problem, then that's pretty much A-level work. Okay? Bits and pieces, well, anything from a C to a B if you got most of them, but don't quite pull them together. But that's the knowledge that we need to have.